Hi everyone. Today we're going to review inverse functions. And in the next video, as you'll see, we will luckily be able to take the derivatives of them. But for now, let's just recall what an inverse function is. Two functions, f and g, are inverse functions of each other. They're inverse functions of each other if, one, f of g of x is equal to x for all x in the domain of g, and two, g of f of x is equal to x for all x in the domain of f. So what this is saying is that if you start off with some element x in whichever domain is applicable here, and then you apply one function and then apply the other one, it has no net effect. So f and g essentially undo each other under composition of functions. Yeah? And typically we'll say that if a function g satisfies this, we will have that g of x is called f inverse of x. G of x is called f inverse of x. And what this means is that if y is equal to the value of f at some point x, then that's equivalent to saying that x is equal to the inverse function evaluated at the point y. So y is equal to f of x if and only if x is equal to f inverse of y. Yeah, and this is how you can go back and forth. Let's recall when a function has an inverse function. When do we have an inverse function? We need to have that notion of a horizontal line test, if you recall from pre-calculus. It passes the horizontal line test. If, whenever f of x equals f of y, we must necessarily have that x is equal to y for all values of x and y in the domain of f. Yeah? So what does this mean? If the outputs of the function are the same, the only way that can happen is if the two inputs were initially the same in the first place, right? And that's our intuitive idea of the horizontal line test. Let's draw some pictures just to make sure that we remember what the horizontal line test does for us. If our function looks something like this, then if I pierce the function horizontally, it only passes through the function exactly once. If the function curves back on itself, then if I pierce horizontally, it passes through it at least once. And it could be more than twice here, right? I mean, if I draw maybe a little cubic function like this, down here it only passes once. But here it looks like it passes 1, 2, 3 times. Yeah? So it could pass once during some portions, but there will be some values if it fails a horizontal line test, there will be some function values that are achieved by different input values. Yeah? What's really interesting here, what do you notice about the slopes of this function? What do you notice about the slopes of this function? They're all positive, right? What about the slopes of this function? I see that first we have positive slopes of our tangent lines, and then we go to negative slopes. Here it's positive slope, positive slope, positive slope, negative slope. Do you see it's decreasing here? And then we go back to positive slope. But the idea is that there's going to be some relationship between passing the horizontal line test and the derivative. There will be some relationship. Before we talk about that relationship, let's define a certain type of function. A function that passes the horizontal line test will be called injective. Oops. That's injective. Yeah. If you don't like the word injective, you'll also hear the word one-to-one. Yeah, there's a one, for every y value there's exactly one x value, and vice versa, of course. Okay, so let's redraw those pictures. We know that if I have a function that passes the horizontal line test, we generally want it to look something like this. Or it could also look something like this, right? There's another function that perfectly passes the horizontal line test. Let's write down a true statement. Here's a fun fact for us. If f is a continuous function, and if f prime of x is always bigger than 0, or f prime of x is always less than 0 for all x in the domain of f, then f of x is injective. Yeah? What's this saying? If f prime of x is strictly larger than 0 for all x in the domain of f, that's this case here, isn't it? The slopes of all the tangent lines are positive. We're always strictly increasing. This is the case where f prime of x is strictly greater than 0 for all x. In this case, it looks like f prime of x, the slopes of all of our tangent lines are negative. We're decreasing everywhere, right? And this is going to be kind of nice for us. Let's do an example. Let's determine whether our favorite function, f of x, equals to negative 5x plus 3 is injective. Determine whether this function is injective. Pause the video. Make sure you understand how to do this. Okay, so let's just try to take a derivative, right? What's f prime here? It's negative 5. Negative 5 has the wonderful property of being strictly less than 0 for all values of x in the domain of f. And the domain of f here is all real numbers, of course. But for all real numbers, negative 5 is less than 0, right? So that's kind of nice. It is an injective function. So what does that mean for us? Because it's injective, it must pass the horizontal line test. What does that mean? The inverse is a function. So the inverse is a function. It is a function. Let's remember, how do we find the inverse? We know that it has an inverse. We know that it's going to be a function. How do we find it? Well, instead of having y equals negative 5x plus 3, remember we construct inverse functions by swapping the roles of x and y in this equation. So instead we're going to have x equals to negative 5y plus 3, right? And now we solve for y. Solving for y, first we can subtract 3. We get negative 5y equals x minus 3. Dividing by negative 5 tells us that y equals to negative 1/5 x plus 3/5. And this is our inverse function. This is f inverse of x. Yeah? What does it mean again to be the inverse function? Let's just remember and try this for yourself. Verify that f of f inverse of x. So what does this mean? We take f inverse of x, this function, and wherever we see x, we replace it with f inverse of x in this function, right? So this is going to be negative 5 times f inverse of x, which is negative 1/5 x plus 3/5 plus 3. Yeah? And make sure that you see that this is, in fact, x. Yeah? And similarly, if we compose the other way, f inverse of f of x, in our equation for f inverse of x, wherever we see x, we will plug in f of x, yeah? And we'll see immediately that this gives us negative 1/5 times negative 5x plus 3 plus 3/5 is indeed x, and that's kind of nice for us. Yeah? So they are inverse functions. And this is indeed a function, right? We know it's a function because it's, f of x was injective, and we can see that it's a function because it's a nice linear equation, right? All right, let's do another example. Determine whether f of x equals to x cubed plus 2x minus 13 is injective. Pause the video. Make sure you know how to do this. So, just like in the last example, let's take a derivative, right? F prime of x, in this case, is going to be 3x squared plus 2. I know that 3x squared is always bigger than or equal to 0, and once you add 2, you are strictly greater than 0, right? Yeah, and of course, since f is continuous, what does this mean? It means that f of x is injective. F of x is injective. So let's try to construct the inverse function. Yeah, how do we construct the inverse function? If we have that y is equal to x cubed plus 2x minus 13, how do we construct the inverse function? We swap the roles of x and y. That gives us that x is equal to y cubed plus 2y minus 13. And now we solve for y, right? But there's an issue. That's an extremely unpleasant task here. Yeah? And indeed, in many functions, you will not be able to explicitly solve for y. Yeah? So we know that there is an inverse function, but writing it down explicitly is not always possible. Yeah? We cannot, in this case, find, certainly not easily, what the inverse function is. Yeah? But nonetheless, let's see if we can do something with it. Let's figure out if we can compute f inverse of negative 1. And we've already said that we can't find the function f inverse of negative 1. How could we have a chance of computing the function value at a certain point? Well, let's remember that if this function is some value x, remember we had our duality, f inverse of y equals x, is the same as saying that f of x is equal to y, right? So if f inverse of negative 1 is x, then that really means that we need to find a value of x such that f of x is negative 1. How can we do this? One way to do this, and this does come up on the AP test, one way to do this is to simply stare at the function f of x. Do you see any easy values of x where the output is negative 1? Pause the video, see if you can figure out an easy value of x that outputs negative 1 for you. So I hope you guys found that x equals 2, I think, works here, because what's f of 2? F of 2 is 8 plus 4 minus 13, which is negative 1. Yeah? So if f of 2 is negative 1, what does that mean for us? That means that f inverse of negative 1 has to be the value 2. And this process of staring at the function is called by inspection. By staring at the function, by inspecting the function, we found a value x that outputs a y value of negative 1. Yeah? But I know what you're thinking. Boy, gee howdy, how can we find derivatives of these functions, right? We may not even be able to write down the equations for the inverse function. Do we have a chance of even being able to take a derivative? Let's see. let's first let f of x be differentiable. Oops. And have an inverse function, f inverse of x. Yeah? How can we compute? Our goal here is to compute f inverse prime of x. And that looks like a hot mess, I know. It's the derivative of f inverse evaluated at x. Yeah? Let's rewrite this another way that might seem more familiar to us, given our understanding of implicit differentiation. It's asking us to find dy dx if y is equal to f inverse of x. Yeah? Find dy dx if y is equal to f inverse of x, sorry. And you say, I don't see any implicit differentiation here. But let's take f of both sides. Let's take f of both sides. Remember that if y is equal to f inverse of x, this is equivalent to what statement? This is equivalent to saying that f of y equals x. And now we can perform implicit differentiation. So now let's differentiate both sides. What's the derivative of f of stuff? It's f prime of stuff, right? Times the derivative of what's inside. Well, what's the derivative of what's inside? It's dy dx. And the derivative of the right-hand side is 1. So what does that mean? That means that dy dx is equal to 1 divided by f prime of y. But we have a y in here. That's no fun. Really what we have is that dy dx is equal to 1 divided by f prime of, what's y equal to? Y is f inverse of x, yeah? So it's the derivative of f evaluated at f inverse of x. Yeah? And here is the formula that will always work, but the method behind the formula I think is even more important. How we derive it is more important, how we derive this formula. Remember, what's the idea? We start off with y equals f inverse of x. We use the function of inverse properties, and then we simply apply implicit differentiation. And that's pretty easy, yeah? Truth be told, I don't remember this formula offhand. I always remember, though, how to derive it. I always remember how to derive it. So let's do an example. Let f of x be our favorite function, x cubed plus 2x minus 13. Let's compute f inverse prime of negative 1. Remember that in this case, we can't simply compute the inverse function and then take a derivative and then evaluate at negative 1, right? If we could, then that might be easy. But in this case, we can't go and fetch the inverse function to take a derivative directly. So instead, let's use the formula that we just derived. We know that f inverse prime of negative 1 will equal to 1 divided by the derivative of f evaluated at f inverse of negative 1. And now we work this inside out. We start at the inside and work our way out. What's f inverse of negative 1? We saw in a previous example that that was 2. Because 2 cubed plus 4 minus 13 is negative 1. Now we simply need to compute f prime of 2. Well, what's f prime of x? It's 3x squared plus 2. So what's f prime of 2? Looks like 3 times 4 plus 2. And so the derivative of the inverse function at negative 1 is 1 divided by 14. Alright guys, I hope that this helps. You now have everything that you need to work the worksheet on inverse functions. I'm going to post a review on inverse trigonometric functions that in case you need a review from trigonometry, and then we'll talk about in the next video together how to take derivatives of the inverse trigonometric functions. So if you have any questions, feel free to reach out via email, and I'm happy to set up a time to Zoom with you if you'd prefer that. And I look forward to seeing you in the next video. Thanks so much.